Hello everyone. So today we are going to do Leetcode daily challenge, longest increasing subsequence. And in this solution, this video would be a bit lengthy because I'll let you know about the recursive, memoization, bottomup, and even the binary search solution for the same. Means basically n square and Nlogn, both solution I'll show you. So now let's get started from the question itself. Let me show you the question, that what it means. So here's the question. So given an integer array nums, return the length of the longest strictly increasing subsequence, and a subsequence is a sequence that can be derived from an array by deleting some or no elements without changing the order of the remaining elements. For example, 3, 6, 2, 7 is subsequence of the array 0, 3, 1, 2, 6. So here the thing is that a subsequence could be the whole array itself, means this whole would be one subsequence itself, or if we just choose any of the elements which are being there by skipping these elements, then also the remaining elements will become a subsequence provided they all are in the order, the way here it is. If it would have been written like this, then it wouldn't have been a subsequence. So that's the thing we want to let us know. So now let us first check about the first example which is being here, and before that let us check for all the constraints which are given to us. So here the first constraint is nums length, that is up to 2500. That is basically length is pretty much smaller. These elements which are being given to us, they are pretty much smaller. So in that all scenario, we can use a DP solution here. But the recursive solution, that is exponential one, won't work to much extent. Although we can let it work with some modification, but still it will give TLE in some of the test cases here. And each element which is being there, basically what I refer by element here is each integer, because it is integer array, is here 10 raised to power 4. Its smallest one would be minus 10 raised to power 4. So they have given us follow-up that could we come up with Nlogn solution, and the answer is yes, we can easily come up with Nlogn solution. When we'll go ahead with the binary search approach, then we can. So now comes the part. Let's start with the question that how we can do it. Basically, let me first show you that how you need to think about this question. So now here comes the part that we are given with this first array, right? Now we need to figure out what is the longest increasing subsequence. Basically, subsequence we are required to figure out that what all subsequence are, but that subsequence should be in increasing order. In this particular array, there are two subsequences, that is this blue one and this brown one. These are the two subsequences which are longest in nature, but other than that, there are other subsequences as well. See, this 3, 7, 101, it is also a longest increasing subsequence. Then this particular 5, 7, 101, it is also increasing subsequence. Then this 5, 7, and then 18, it is also an increasing subsequence. Then 3, 101 and this 18, or not 18, but if we discard this 101 earlier we are taken, if we take this 3, 7, 101 and then 18, then it is also a longest, not longest, but increasing subsequence. Now in all these increasing subsequences, because in the question we are required to find longest, and the other word is increasing, and the third word is subsequence. So in that context, first we are required to find all the increasing subsequences, right? If we need to code our solution in such a manner that we are able to figure out with the increasing subsequences, and out of all those increasing subsequences, we need to figure out with the longest one. So this is the thing which we are required to do in a question. And now comes back that how we will be able to figure out with increasing subsequence. So first we are required to go with that. So in recursion, because here we'll going by the recursive. So in recursion, how we'll going would be, we'll see if we take this element, right, and then go ahead, and then we'll check for which one out of the other is the greater than this particular, right? So we'll only get this one or this one, right? If we take this one, then we'll go ahead and check for which one is greater than this one, right? Like this only we'll do for the each and every integer which is being present here, right? So what we are doing is that we need to either choose or not to choose the present element. That is the thing which we are doing here. Basically, we are required to make choices on this basis, that either we need to take this element or we are not required to take this element. So like that only our recursive tree would be like this, means this whole array would be given, and for each, and we'll go to each index and we'll check, do we need to take this element? Yeah, we have taken, or not want to take this element, then this would be blank. Then we'll take the next element, yeah, then we don't take the next element, so that's only 10 is there. But here we just checked that it is smaller than a previous element, right? So that's why this sequence would be discarded, and like this only whole recursive tree would be formed. And because we are either taking or not taking, that's why the recursive solution time complexity comes out to be 2 raised to power n. And the space complexity, that would be directly equals to n, because at max in our stack there would be n elements only. So that's why these are the time complexity and space complexity of a recursive solution. Now you have somehow idea about how the recursive solution would be. But next part of this question is that how we are required to code this recursive solution, because after coding the recursive solution, then only we can do the memoization step. So that's why here comes the part. So for a recursive solution, there are 3 things which we require. These 3 things are there. So now, before going ahead with the base case, we are required to know that what is the recurrence relation, so that according to that we can make our base case. And before going ahead with the recurrence relation, we are required to check that what are the choices which we are required to make, so that we can come up with a recurrence relation. So choices in this are either we are required to take it or not take it. So that are the 2 choices which we will be making. So according to that only, we will write a recurrence relation, and recurrence relation would directly influence our function of the recursion. So it would be like, we'll go ahead with I and previous index which is being there, or not index only, not index but the element. So according to that only we'll do and go ahead like this. If we are not taking, then we'll write our function, increase our index and carry forward a previous element which is being there. And if we take the element, then we'll increment the count that we have taken this element, and then we'll increase the index so that we could move ahead, and we'll carry forward, and we will carry forward our present element, so that now this could be chosen as previous element to our next subsequence. So that is the thing which we are doing here. Now comes the part that what would be the base case in all this scenario. So this recurrence relation would hit a base case on this particular thing because of the length of the array. So as we are moving ahead, So at some point we'll reach the size of the nums array, means all the elements would be exhausted. So at that scenario, means when it reaches at this point, we'll return 0, because now we are not left with any element, so there are no choices left, so that's why we'll return 0. So this is all about the reconciliation based case and the choices for a recursive solution. Now comes the part that how we are required to memoize this solution. So for memoizing this solution, we are required a 1D memoized data structure so that we could keep the check of the previous element which was there, because this particular I plus 1 thing which is there, it will be easily handled by the function itself, but we are required to keep the track of the previous element in our memoized data structure, and that would help us to avoid all the repeated subcases. So that's why we would be using something like this, means at every stage we will be using something like this, and this would be either we could take a vector or array, that's all our choice. In C++ and in Java and other languages accordingly we can choose. Now comes the next part, that after this recursive and memoization, now comes the bottom-up DB. For bottom-up DB, we are required with two things. One is state and transition, and second is transition. And the base case would be handled accordingly in the question itself, means the solution. So a state is basically a one-dimensional array only, in which I is there, and I basically represents the present index which is being there for that nums array, and the transition would be something like this, that we are required to figure out with the maximum numbers. Maximum number here refers to maximum count which we could get for the subsequence for the DP of if the present one is already the maximum, then this would be selected, or if other one by adding 1 to it, if that is the one which is greater than the value of the previous node, then that would be selected. And this is on the condition that a nums of I is greater than nums of j, basically when we encounter a new subsequence. So for that scenario only we will be going ahead with this transition. So this was for the bottom-up solution and about the binary search. Now comes that part. About the binary search, so how we'll go ahead with the binary search. So the thing is, for binary search, we are required to go ahead with 3 steps. And those 3 steps are like this. Okay, first I'll explain you, then I'll show you with the code that how they are. So for those 3 steps, they are extend, reduce, and the other one is replace. So in the binary search, what we are doing, we would be extending or we will be replacing. That is the thing, not the reducing part. This is the thing, and then we'll return the length, because at the end we are required to return the length. So this is the thing which we would be doing in our binary search approach. So how this thing goes ahead with is, see, the thing is that we'll play with the index the way we were playing earlier also, right? Means we are given with that, if I take that example only, means of that first example, in that we were given with 10, 9, 2, 5, 3, 7, 1, 0, 1 and 18, right? So now the first thing would be that we will be having our LIS vector which we will be passing. This is our auxiliary phase which we are taking by R, and the present element will pass this one, and this will act as a target that we would be required, because in the binary search we will be searching this target element, that where we are able to figure out this element, and according to that only we will be going ahead with our subsequence for being in increasing order. Now here, as we will be going ahead with all our index, because in that particular binary search which we will be doing, in that what we will be doing is that binary search function would simply return our index, and that index would be the index of this target. So according to that index only, we is required to figure out that are we able to find that particular element or not. If we are not able to figure out with that element in that particular space, then we'll extend our LIS, else we will replace our LIS. That is the thing which we would be doing in our binary search solution. I guess that you'll get to know more about when I'll show you the code. So just we need to keep in mind about the extend and the replace principle while using our binary search approach. So now let me show you the code from the starting, and starting that refers to from the recursive solution. So for the recursive part, what we are required to do is our main function is this, means our recursive function is this, and our main function is this. We are directly writing a recursive function where we are passing this num, our index, and the previous element. We are taking it as int min. Now comes the part. This is our base case, and this is either we want to take it or we don't want to take it. If we are not taking it, then we will be going ahead with this function. If we are taking it, so we'll first check that if our nums of I is greater than previous. If that is the case, and in that scenario, we'll increment the count, and then we'll call the function with our number of I, which will now act as our previous element to the next element. So that is the scenario which we will be doing here. Because when we were making that, means take and not take, right? So here blank was being passed in. So blank simply represents that we are just passing our previous element, and here previous element is int min. That is the thing which we were doing, and here 10 is being passed, right? So this particular 10 is being passed here. So that is the thing which we are doing here. And I plus 1 simply represents that we just want to go ahead with the next number, and 1 is being incremented because now our length of LIS is 1. So that's why 1 is being there. So this is what we are doing in this particular solution. Now comes the part at the end, that basically we require maximum out of both of them. Yes, because we require the longest one, because these all would let us know about the increasing subsequences. So that is the thing this will tell. But this will tell us about the longest one. So that's why we are doing this. So this was for the recursive solution. Now comes the part for the memoization. So in the memoization, everything would be same as we were doing in the recursion. Only thing is that we have defined the DP here, and that DP we are taking as per the size of this nums array itself, plus 1. Plus 1 is basically for the base case, and minus 1 for initializing our DP array with everything which is being there. And now comes the part that how we are required to use this DP array. So for using this DP array, we'll use like this, that if it is not equals to minus 1 means the initial stage. If it is not like that, then we'll return this one, else we don't do anything. And now we'll take this in take and don't take, and then if previous of I is equals to minus 1, or nums of I is greater than nums of previous of I, then in that scenario, we will take, that is 1 plus solve of this, and at the end we will return maximum out of take and don't take. So now, sir, why we were taking this particular thing, why we were checking for this particular thing also, because the previous of I was directly passed with this -1. If it is the starting mode stage only, then also we are required to take that element, right? So that's why we were doing this particular step. So this is how we were doing this particular question for recursion and memoization. Now comes the part for a DP solution of bottom up. So here at the starting we are taking answer equals to 1 because the starting element itself would be counted, size, and then our DP array which is there, which is one dimensional and would be filled with all ones. Now we are taking nested loop, and this second loop will be going till I only and would be starting from I equals to 0 and would check each and every element. Now there is a condition that this particular transition would only be done if our nums of I is basically greater than nums of j. And if that is the same, that is we are able to figure out with a new subsequence, then only we'll check that is it maximum or previous one is maximum. And here only we'll update with the answer, and it will directly pick up the answer according to the fact that if the previous one was bigger, so it will remain as it is, else it will update with a new one. And at the end, we are required to return our answer. So this was for our DP solution in bottom-up manner. Now comes the part for our binary search solution. So here now I can better explain you that what I was saying about the extend and replace. Now, at the starting, because we want to start with a binary search and it is the first element, so we will directly push our first element to our LIS. And now in this particular, what we are doing is, we will be first checking our index for this particular element in this LIS, and that index would be returned here, right? And if we are unable to figure out with the element, means if that is not there, then we will push here, and if it is already there, then we will replace it. This is the thing which we would be doing here. Now let me show you that what exactly I mean here. So now here comes the part that I will be doing this binary search here, right? And answer equals to int max. That is, at the starting we will be taking the greatest one so that we could easily compare. Now doing a simple binary search the way we do for avoiding the overflow. And now here comes the part that LIS of mid is, if LIS of mid is greater than equal to target. Our target is the number of I, and here we are trying to figure out with the lower bound. And what does lower bound mean? Lower bound simply means the element which is smaller and greatest of all the smaller elements. Means it is just smaller from the given element. That is the thing here. So here answer would be minimum out of answer and mid. So it is already int max. So this will help us to get whatsoever element is there at the mid, right? So that would be updated in an answer, and our right most would be directly moved towards starting point. Else, if this is not the scenario, then our left would move towards the right side. And now here we are required to check that if answer is not equals to int max, then only will return the answer, else we will return -1. So the thing is, then when -1 is being returned, that is our answer was not updated. So in that scenario, we will directly push that particular element to our LIS, else we will replace the element. The replacing part takes place whenever we are able to figure out a new element which is being increased, which will give us a new array which would be increasing in nature. Basically, the previous element which was there, that would have been the greater one, and now we are able to figure out with a new element which is a smaller one than that. So that's why we are required to replace the element so that we could figure out with a new subsequence. So that is the thing which we would be doing here. So this was all for a binary search approach. And the time complexity for the binary search approach is order of Nlogn, and the space complexity is order of n because of the LIS array which we are taking. So this was all for this question. If you have any doubt, you could comment it down, and please do like and subscribe our channel if you really like the way I have explained you all the solutions and questions. Thank you.